Right. So my friend Tim and I are going to um, have like this sort of um, video blog on philosophy and science stuff, or at least that's the plan right now. So we want to go over Michael Friedman's Foundations of Spacetime Theories first. Uh, I guess I'll just introduce us first. So my friend Tim Prisk, he's been a friend of mine for many years now. I think maybe 9 or 8 years. Uh, we know each other from social media, but it's pretty cool friendship. And he is a PhD. He has a PhD in physics. Um, who also he also has he also went to college to do a study both physics and philosophy. He went to UMA Summers, which is where I'm studying my PhD actually, and work with some of the people that I'm working with. And he has interest in both physics and philosophy. In philosophy specifically, he has interest in uh, philosophy of science, epistemology of science, history of philosophy, philosophy of language, and philosophy of logic, and specifically the applications of philosophical logic to the analysis of uh, propositions and paradoxes and the just logical inferences in general. And as for me, I am. And I guess I also wanted to mention that he has done some. He has worked in the past in the NIST and in Oak Ridge Lab as doing experimental work in physics. So I have some. So I want to have the opportunity later on to ask him some questions about his experimental work and how experimental physics works, because I guess this is a parenthesis, but one thing that I guess I'm curious about is just we hear a lot, people who are reading about physics in the media. We hear a lot about how theoretical physics, I guess, works, but not so much about the experimental work and all that's the stuff that's involved in testing hypotheses. So that's something that I'm very much interested in talking to Tim about. But he's definitely going to, help me understand some physics ideas in this book. But well, as for myself, I'm a philosophy PhD student at UMA Amherst. I also have been doing some research as a master's student in philosophy of science at UNAM. I wrote my thesis on persistence of material objects in classical and relativistic spacetimes. So the question there is, how do material objects persist in those spacetimes? And I got my college degree at UNAM in Mexico too. And one of the subjects that I worked over there for my college degree was the philosophy of Bertrand Russell. So those are still like some of the two major areas of interest that I have. Is just philosophy of space and time, and the philosophy of Bertrand Russell, specifically his philosophy of mathematics and science. And lately, just more general metaphysics problems and problems of the methodology of metaphysics. So Tim, do you want to say something about your interest in the Friedman book?
Yeah, there's a number of reasons I wanted to take up reading this book and thinking about Friedman's ideas. The first is that a kind of personal reason. The theory of relativity is what got me interested in physics in the first place. I think it was 13 or 14 years old in the public library, and I happened to pull off the shelf a little volume by Feynman called Six Not So Easy Pieces. And it's the chapters of that book
Here's the
are
book.
six. Yeah, that's the one. There are 6 different chapters taken from the whole Feynman lectures on physics, and they're focused on both the special and general theory of relativity. And I just thought that was just very exciting stuff, and that got me started on physics to begin with. So I happen to really like the subject, and I want to understand it more deeply. I studied the general theory of relativity in my coursework in graduate school, but I've never actually done any work in the subject. So there's certainly plenty of room for me to grow, and that's one of the reasons I was interested in this book, especially because Friedman is approaching it from the standpoint of a philosopher. So he's going to pay close attention to its conceptual and mathematical foundations. And that's one way of enriching and deepening your understanding of the book or of the theory. Also, I wanted to understand some more about the history of philosophy and some of the key ideas in the philosophy of science. As Friedman talks about, the theory of relativity was a major stimulus to the modern philosophy of science, to the development of logical positivism. And it's really not possible to understand those movements apart from their relationship to Einstein and Einstein's ideas. My past exposure to logical positivism has been, I would say, relatively superficial. I read A.J. Ayer's Language, Truth, and Logic, and saw logical positivism only from the point of view of the philosophy of language, where you kind of take on the verifiability principle as a kind of theory of meaning in language. And I might be mistaken about this, but I have the sense that that's not really the essence of logical positivism. They didn't really set out to make a theory of language or a theory of semantics, but they were led to thinking about language because of the problems that they were considering.
Yeah, yeah. I mean, just as I guess as a parenthesis, but this is something that actually comes up in the chapter we're going to talk about. I mean, I entirely agree that it seems that there's a motivation from the epistemology of science for introducing these theories of language. But anyway, you were going to say something else.
Oh, I don't think so. I think I was going to ask you what interests you in this particular book. There's a lot of material about relativity, especially in philosophy. What attracted you to Friedman in particular?
So I guess, I mean, um, yeah, as you mentioned, there are a number of books that I'm interested in reading. This is just one of those books, but this is one book which I had like a special interest in going through because, oh, so I guess there are three reasons that come to mind. So the first one is just the level of, technical mastery that Friedman exhibits when presenting like the general discussion of the structure of space-time theories. He does it at a sophisticated level. Still not overwhelming for philosophers of science, I think. So Friedman, like most philosophers, philosophers, we usually are concerned with the most general features of some of the systems that we're studying. So sometimes we don't really get into the calculations of some of the theories that we are looking at, but we certainly are interested in the general mathematical properties of these theories. So I have already read, because of the fact that I wrote my master's thesis on persistence in classical and relativistic spacetimes. I have already read some of the introductory material on these issues, like for example Mauchlin's excellent, highly recommended Philosophy of Physics, Space and Time. Some work by metaphysicians who have a mastery of some of these concepts, such as Yuri Balashev, his Persistence in Spacetime, and other related material. And I had also taken, I mean, I have also read some other, essays by or papers by Motley and people like Hofer, etc., on space-time theories. Both, for writing my master's thesis, and also recently I just took a graduate course on philosophy of space-time, and we looked at some of the classic papers on the subject. From Newton's bucket argument to more recent stuff. But still, all of that is mostly treated at a philosophical level, which, even though it assumes even though it has some technical complexity, uh, it it doesn't go above certain level. And I felt like I wanted to go a bit deeper into the subject at the mathematical and conceptual level. So that's the first reason. The second reason is just Friedman's reputation in general among philosophers of science. So Friedman has written a lot on not only philosophy of science and general philosophy of science, the problem of realism, the problem of theoretical versus observational entities, and so on. But he also has written a lot on Carnap's philosophy of science, on the logical construction of the world. He has written on Russell's philosophy of physics. He's co-author together with William Dempoulos, of one of the classic papers on Russell's philosophy of science. Uh, and all of the work that I've seen from Friedman is just first rate, philosophically speaking. So that inspired me to want to read this book. And I guess the third reason will have to do with the stuff that Tim also mentions, which is, just having more insight into the connections between logical empiricism or logical positivism and its impact on philosophy of science, as well as the impact of science on philosophy, which is clearly reflected on the concerns and preoccupations and methodologies of the logical positivists. And I think that because Friedman has a really good grasp, for the reasons I just mentioned, of both space-time theories and physics, and the philosophical aspects of physics in general, and the history of analytic philosophy, that this will be a good book to study to deepen my understanding of those two subjects that I'm fascinated about. So yeah, those are basically the reasons.
When you were talking, I remembered I had a kind of third reason.
Mm-hmm.
And I think as science develops, we learn more about what good science is. We learn more about what a coherent, rational understanding of nature is like. And the general theory of relativity is a kind of paradigm for that, I think. In a way, Einstein didn't just teach us the theory of relativity, but he taught us something about science and how to do science. And I would like to take away any relevant lessons from relativity to thinking about another pillar of physics, namely quantum mechanics. Now, I looked in the index of Friedman's book to see how often quantum mechanics is going to come up, and it occurs exactly twice, mentioned in passing in footnotes. So we won't hear much about quantum mechanics, or really at all, from Friedman in this book. But I think it would be interesting if we can apply some of the lessons that Friedman draws from the general theory of relativity to thinking about quantum mechanics. And there's also, for me, a kind of historical question about understanding Einstein, which is maybe a little tangent to some of the issues Friedman is going to raise.
Mm-hmm.
But Einstein interacted a lot with the logical positivists during his life. And at some periods, he seems to respond to them favorably. And then later on, he seems to be opposed to them. And some people have interpreted this as meaning that Einstein was a kind of positivist or positivist sympathizer early on, and then he transitioned to being some kind of a realist later on. And I don't know if I really think that Einstein's writings support that kind of reasoning or that
Right.
kind of interpretation, but I'm not sure I could really show convincingly that it's not right. So I'd like to have a little deeper understanding of him. And also,
As a philosopher of science.
yeah, as a philosopher of science. Um, and in relation to quantum mechanics, why is it that Einstein um, was so dissatisfied with quantum mechanics? I mean, part of the answer we know, and it's not a space-time theory. Einstein says that the foundations of physics should be along the lines of classical field theory. And in one place, he says that he wouldn't regard quantum mechanics as complete, even if it was made consistent with the general theory of relativity. So
Interesting.
even if there was a quantum theory of gravity,
Mm-hmm.
maybe Einstein wouldn't be convinced. So there was obviously something deeply compelling to him about classical field theories that made him believe that that should be the foundation of physics, and that the general theory of relativity was kind of a model for what a good theory should be.
Yeah,
And
I didn't know that. That's actually very interesting. So I mean, I guess I'll just make like a comment before maybe moving on to some discussions in the Friedman, but this is relevant as well to obviously the whole point of doing this, right? So I guess one thing that I'm intrigued by that is there's recently some literature in the philosophy of quantum mechanics that tries to defend the idea of classicality in a methodological sense. So for example, the idea that we won't have a satisfactory theory of the quantum world until we can understand it in classical space-time terms. I guess that's one way of putting it. So I'm thinking, for example, of programs, and I hope I'm not misrepresenting some of these ideas, but we'll come back to them later. But so there's this research program by Balia Lori, a philosopher of physics. She has this idea that we should think about the primitive ontology of the theories. So uh, we can consider what quantum mechanics says about the world and understand it better if we try to give quantum mechanics a sort of primitive ontology. And what does she mean by that? She means something very similar to, I guess, what John Bell called local bubbles. Just like positing material stuff in space-time and telling us how it evolves with time. Like the dynamical evolution of that material content. And then she goes on to talk about the different ways in which some interpretations of quantum mechanics, like GRW, have posited primitive ontology. Like, for example, have incorporated, typical GRW doesn't have primitive ontology, but there are like these extensions that have what are called flashes, a flash ontology or a mass density ontology. And the idea is to presuppose some sort of classical spacetime, and then the wave function is like this, this law-like property of the theory that tells us how those material contents of the 3D space evolve. But part of I guess the point, the relevant point here is, what is the motivation? What is the methodological motivation that she has for doing this? And the reason is that she thinks that it's important that science, when we're doing science, that we understand what we're doing. So we have to have some understanding of the theory in order to be successful, even as scientists. So, and it's, space-time theories are, I guess the thought is that space-time theories are much more intuitive to us than the picture, than I guess the somewhat obscure picture to my mind that quantum mechanics gives us of how the world is. And you see, I mean, just as a last comment on this, but you see this motivation not only in people like Allori, who's a philosopher of physics, but also in people like David Lewis. So, for example, his idea of human supervenience, that you can think of some worlds, you can think of everything that happens at a world as the result of whatever happens at the fundamental level at that world. So the basic idea is that if you have a space-time world, with points, and you can give the fundamental part distribution of the distribution of fundamental properties at those points, just as field theory does. Then everything else in that at those worlds that are like this supervenes on that distribution of fundamental properties at those at the space-time points. And it seems like Lewis's motivation was exactly the same as Allori, at least if my reading is right, that these theories are easy to understand, or we're in a better position to make sense of what these theories are telling us the world is like than standard quantum mechanics. So I do wonder, I guess, in connection to that, whether there might not be some. So I guess I have two questions. I guess I'm thinking, what are your thoughts on this? But one of the questions is, first, do you think that Einstein had similar motivations? And second, do you see some analogy here or some similarity between these views and something like the Kantian view that Friedman also discusses in the book, that there's something about a spatial representation or a spatiotemporal representation, which is unique to our ways of the way our minds work. So obviously Kant wasn't thinking of anything like cognitive science or anything like that, but Kant did have this idea of space and time as the apodeictic forms of of the of representation of order and geometry. So basically for Kant, the idea was that we had to impose some sort of structure on the world, and our minds always impose a geometry and an order on which things happen. And from the geometry you get space, from the order you get time. But this is stuff that the mind necessarily puts into reality. It's not really out there. But I guess for Kant, it just seems so clear that these things were put in by us, that a lot of the way we seem to understand, we seem naturally inclined to understand the world in spatiotemporal terms. So I guess I'm just interested just hearing your thoughts in general about these connections between understanding and spatiotemporality, and why some people think that they are necessary for scientific understanding in general, or scientific representation.
Yeah, that's a big question. And of course, Kant is going to loom large in, the chapter today. I think Kant's idea that space, time, causality, matter are kind of essential to constructing an intelligible picture of the world has been received by a lot of different people. For example, to pick someone in philosophy, there's Peter Strawson. If you look at his book, The Bounds of Sense, which is about a commentary on Kant, or about individuals, Strawson does say it's part of our way of individuating things, that we can view them as kind of localized in space-time and distinguished in space-time.
Right.
That this thing is one individual and that thing is another individual, is kind of basic to our kind of conceptual framework, for lack, I don't have a good word for it. You get a variant of this in Niels Bohr. I think probably the most difficult and obscure part of Bohr and the Copenhagen interpretation of quantum mechanics is the role of the classical level.
Mhm.
Bohr always insisted that our measuring devices and measuring instruments should be amenable to a classical description. And in some sense, I think that that's right. But when you put a little pressure on that and ask what a classical description is, it's not entirely clear. Bohr is sometimes read as a kind of naturalized Kantian, where space, time, matter, and causation are kind of a practical a priori that we bring to doing experiments. I think Heisenberg even says something like that in Physics and Philosophy. And of course, there's Einstein himself, who wanted to use space-time theories as a foundation for all of physics. I think a lot of these issues about individuating things by space-time localization does come up in quantum mechanics, certainly with entanglement, but also with Bose and Fermi statistics, where it becomes unclear how you would individuate objects because you're kind of losing a space-time description of them. And I think that's a source of a lot of vexation about the theory, that it kind of runs completely against the way we're inclined, maybe necessarily inclined, to think about nature.
Right. Yeah. I mean, so I guess, yeah, I guess what bothers people is that I guess this is something that will keep, a subject that will keep coming up, but something that I guess bothers many philosophers and even scientists is the idea just that we cannot even imagine or clearly grasp what a world, just to take an example, right, that function as, standard quantum mechanics says the world works, will be like. It's not that clear how we can picture that on the one hand. Whereas on the space-time picture, we at least have, I guess, some analogies on the one hand, some metaphors which are very, I guess, easy to grasp. We can imagine a space and putting objects over there and those objects changing their positions with time, etc. We can certainly have this mental imagery. And we also have, like the mathematical way in which the representations connect to that geometry are very intuitive. So like we can imagine a field, covering the whole space-time, and we can just represent that by as a sort of assignment of properties of the field to points of space-time. And that's not so easy to do for the quantum case. So I guess that's part of the allure of that we can make sense of it. But I guess one of the things that's implicit in that, which I find peculiar, and I guess also worth discussing as we move forward, is this notion that the world should be intelligible to us, like at the fundamental level. So maybe it's right. So I guess this is like a dilemma, right? That I think could come up, might be worth asking. Uh, well, not really a dilemma, but maybe it's true that we do need, for theory making, we do need to have some sort of uh, easily graspable representation of the phenomena we are studying, given our limitations, given what sort of beings we are. Maybe that part is right, but it doesn't follow from that the world should in any way conform to our cognitive limitations or prejudices, or so it might be that the world really is very fundamentally strange, but the parts that we can actually grasp have to be intelligible to us in some way. And so that's the struggle. But maybe we cannot, maybe there's, and this is something Kantian as well, right? Like the limitations of metaphysics, I guess, right? Like how far can we push um, theory or our representations of the world to say that they can actually match reality, right? So
Yeah. I think if we try to pursue that, we might not actually get to Friedman.
yeah, definitely. But I guess this is, I just wanted to mention it as something to that might keep coming up as we read Friedman. So
Yes, I think it probably will. Um, Actually, before we started, we were talking a little bit about originality in philosophy, and I think this is also part of the motivation for this book. I mean, this book was published in 1983, so it's been a while. Um, so, what makes the book? What gives it continuing relevance? And how do you see research and originality in philosophy? I'm not trying to suggest it's not worth reading, of course. But,
no, I think that this is a very important question. So I guess one thing that should be said is that I think that many of the so philosophy is a discipline where, as we were talking about earlier, before we started recording, it's a discipline where people often work on many different subjects using widely different methodologies. So it often happens, that some subjects go in and out of fashion. So I think, for example, for the case of the philosophy of space-time or discussions about the epistemology and metaphysics of space-time, uh, I think a lot of it took place during the period of logical empiricism, which Friedman is very much focused on highlighting, because and this is not mentioned in the chapter, but because of the impact that logical empiricism had in the methodology of science on the one hand, and more importantly because of the impact that the methodology of science had on logical empiricism, right? So um, I mean, this is in connection specifically with the idea of verifiability and observability, and notions like that come up in space-time theories. But so I guess part of the point is that there was a significant interest in the philosophy of space-time at that time for the methodological reasons, for interest in the methodological lessons that you can get from there to the philosophy of science in general. So that was one thing, right? And then people like Hans Reichenbach and Maurice Schlick and Carnap and wrote on stuff that had to do with space-time theories. Reichenbach specifically focused on that. People like Bertrand Russell, who was not a logical positivist, but also wrote on some of these disputes, also was very interested in that. And all of that had its heyday in the 20s, 30s. And after that, which is the period that Friedman is trying to sort of cover, there was like this period where people were sort of agreed about what these theories were saying. And they thought that they supported some of their narratives, which we will mention in a bit, like, for example, relationism and conventionalism. But then it turned out that they were mistaken about that, which is part of part of what Friedman said. So I guess this is important to just put it out there, with that Friedman says that the logical positivists were mistaken in their interpretation of space-time theories and how much evidence they lent to their own worldviews. And then he puts forward, I guess, a new picture of space-time theories, which is more realist in a metaphysical sense, which has a reading in which space-time has certain properties, certain structure, right? And at around that time, when Friedman was writing this book, there were other people like John Earman, who was also writing on space-time theories, and he wrote on the very famous whole argument, which is an argument that we'll discuss later, but it's a sort of argument where you can show that certain theories, for example, relativity, have some problems that are similar to the ones that Leibniz pointed out for Newton before. And that also attracted many people to space-time theory. So there were people asking questions about how to solve the whole argument, and there were people asking questions like Friedman about what was like the real structure of space-time, and what was the methodology for space-time theories. And then that lasted for a few years until I guess people sort of thought that they had worked out what to say about both space-time theories. They sort of agreed with Friedman on the one hand, and what to say about the whole argument. And then it also started to die down. So that was like, for about the last 20 years, there hasn't been that much interest in space-time theories per se in the philosophy of physics community or the philosophy of science community. There's still research going on, but most philosophers of physics have mostly focused these days on the philosophy of quantum mechanics, because there has been a lot of research and interest in new interpretations or in different formulations of the old interpretations. But when you look at some of the work that's been done these days on space-time theories from metaphysics, some metaphysicians have used some of these cases to discuss some new approaches in metaphysics. For example, Shamik Dasgupta, Ted Sider among them. Myself, I'm writing a draft on something like that. And then you see that maybe the methodological lessons that Friedman was discussing were still have a lot, of depth that hasn't been explored. So I guess the main point that Friedman is trying to make about methodology is that arguments, like empiricist arguments in philosophy of science, are important, not even if they don't lead to empiricism, right? Where empiricism is the view that most of our knowledge comes from experience, or or from experimental methods at least, right? So even if most of our knowledge or metaphysics is not empiricist, it can still benefit from empiricist types of arguments. And then I guess the question is, why is this the case? Why are these arguments useful in metaphysics as well as philosophy of science and science? And what lessons can we derive from studying their application in depth in the context of space-time theories in a more technical manner? Because as I mentioned, some of the books that have come out lately on this are a bit less, go into a little bit less detail on technical issues. So that's one of the issues which are important for originality, that there's still a lot of ideas and arguments and thoughts to mine from books like this on general methodology of science and general methodology for space-time theories, on the one hand. And on the other hand, a lot of this work, which is, because it's a little bit more complex, has not been properly internalized by many philosophers working on similar subjects. Properly internalizing important subtle discussions like this is bound to lead to just quality work. So that's what I believe, at least.
Yeah, that makes sense. I remember reading somewhere that Kant was not very satisfied with the 1781A edition of the Critique, or not dissatisfied with the edition, but dissatisfied with people's understanding of it. It is a book with 7 seals, and it's quite sophisticated and complex. And this book is also quite rich in technical material. So of course he came out with a second edition that he hoped would clear things up a bit. Unfortunately, Professor Friedman has not delivered us a new edition of this book. But I did want to mention something from another. I got stimulated to pick up another one of Friedman's books. This one, I don't know how clear that is, Dynamics of Reason. And the problem in this book is to try to identify what a scientific philosophy is supposed to be. And he looks to Kant and he says, well, Kant tried to do it, but it didn't work. Helmholtz tried to do it, but it didn't work. The logical empiricists tried to do it and it didn't work. and what kind of scientific philosophy could we have now?
Mhm.
And he raises some more general questions about like what is the relationship between philosophy and science. And there's a paragraph I wanted to read. I'm sorry that I'm not able to share it on screen, so you'll just have to
Yeah,
bear
no
with.
problem.
But this is how he now sees the relationship between philosophy and science, and it might be useful to approach the older book in this spirit. Here's what he says. From this point of view, it is folly for philosophy to attempt to incorporate itself into the sciences, as a branch of psychology, say, or mathematical logic. For its peculiar role is precisely to articulate and stimulate new possibilities at the meta-scientific level, as it were, and it cannot, on pain of entirely relinquishing this role, itself assume the position of a normal science. For the same reason, it is also folly for philosophy to attempt to become scientific, in the sense of finally leaving behind the traditional conflict of opposing schools for a new stable consensus on a generally agreed upon rules of inquiry. We never know in advance what new paradigms and philosophical meta-paradigms might be needed at a given moment of revolutionary science, and so, in philosophy and in the other humanities, it is always to our advantage to let 1,000 flowers bloom. Finally, it is folly as well for philosophy and the other humanities to regret this lack of scientific status, and, even worse, to seek compensation by attempting to strip away such status from the sciences themselves. We should rather rejoice, along with the sciences, in our fundamentally distinct, yet mutually complementary contributions to the total ongoing dialectic of human knowledge.
Yeah, I mean, I think, you know, we were talking about understanding before, and the idea that we sometimes, what's required of a scientific theory in order that we might be more efficient when using it, or applying it to the world to gain some insight. And then it seems like the intelligibility of the theory might be one thing, right? But it might not be a necessary condition for the theory to be uh, used as an instrument, I guess. But it might be a necessary condition for the theory to be understood metaphysically as saying something about reality. But I guess like a deeper question that we need to ask is that even theories that are more intelligible uh, don't have all their philosophical don't have I guess all their philosophical assumptions just explicitly on their sleeves, and scientific theories are usually involve a ton of philosophical assumptions and a ton of philosophical thinking or presuppositions, etc., etc. So even people, and this is something that we have also talked about, like working scientists, even if they are not per se interested in sometimes in some of the philosophical assumptions, they still bring in some philosophical assumptions with them when doing their work. These might be some assumptions that go into a framework that has been successful and empirically sound, etc., but are still for all that assumptions. And part of the relevance of philosophy and in its distinction from science is that science is perfectly fine. It's going to be perfectly fine if it carries on with its successful research programs. Uh, you know, um, uh, Uncovering or understanding or giving us tools to predict or manipulate what goes on in certain domains. But we as human beings still need or still ask ourselves philosophical questions, or need to ask ourselves philosophical questions to make sense of our reality. And this is something, I mean, so, and this is, I mean, Tim and I, we disagree on many philosophical issues, but I guess one of the things that I will say is that I'm very strongly inclined to realism in metaphysics. So thinking that there's like this mind-independent world out there, and not only that, but that we can design metaphysical theories that actually tell us how that world is, and that they might approach the truth or be farther from that, depending on how good they are. And Tim, I think that, I mean, I don't know what your specific metaphysics is, but I think that you might be less committal than me on some of these issues. Even if you're still sympathetic to realism broadly construed, you might still think that, you know, these scopes that some metaphysicians have are just too much, right? But I think that the quest for understanding what, you know, what science says about the world, and just what we can think about the world, is valuable regardless of whether you have these strong metaphysical views or not. Because if it's not telling you something about what the world is, it at least is telling you something about our relationship to the world. So it's these are questions that we really need to ask ourselves to just to make life, I guess. It adds. I'm not going to say, as Socrates did, that a life unexamined is not worth living. I don't think that that's necessarily true, but I do think that it adds depth and richness to life. To that philosophy is necessary in that sense.
Yeah, I fully agree with that.
I don't know. I mean, I don't know if that's like a good take away from the idea that Friedman is discussing there, but at least that's
Yeah,
part
I
of.
think it is. But I think also it can tell us something about the relationship between talking about science in a scientific way and talking about it in a philosophical way. I mean, I thought that the key expression there was imagining new possibilities.
Mhm,
And you
mhm.
never know when the revolutionary new paradigm might come around. Um, you know, it's always hazardous to make guesses about the course of science, but I guess I'll hazard a guess. Um, I think we're kind of in a Kuhnian period of normal science. We have uh, relativity and quantum mechanics and information theory, and they're all very solid in their formulation and uh, empirically successful and so on. Um, and so at the moment, uh, it's possible for many people to say, well, we don't need to worry about those philosophical issues. But I think it's actually worth thinking about them uh, because there's a real possibility that we will find limitations to our current knowledge. Um, we should, as scientists, try to hold fixed um, the paradigms that we're working with and push
Mhm.
them as far and as hard as we can, because that's what makes them break, and that's what leads to great new discoveries. And at that time, uh, we will have to reconsider the foundations in ways that cannot be anticipated. And having some philosophical sensitivity and having a range of philosophical views available uh, can help us make that step when it does come, as I suspect it will.
Yeah, I mean, I definitely agree. But I also think, I mean, that, I mean, in practice, it's really difficult to just stop, to say just focus on this activity and forget like every, any lingering philosophical doubts, or even forget about philosophy for a second, or even just like aesthetic or moral concerns that you might have, because that's just not how humans work. So, or how the human mind works. So if we, I mean, I mean, people are problem solvers, right? Like human beings are problem solvers, and like one of the typical or techniques for problem solving is just to break down stuff into chunks that are more manageable. But you know, this breaking up stuff apart is not really, it doesn't really reflect, you know, the holistic nature of knowledge or thought in general, or you know, the way in which society actually, you know, because philosophy and science are at the end of the day, they are social activities. So it's not really possible to, I mean, there are periods where people perhaps pay less attention to philosophy, but philosophy is pretty resilient. I mean, it's been around for a long time, and I don't. I mean, people worry a lot about the, you know, the job market, and I think that's. I mean, they are. I'm worried too. I mean, there's good reason to be worried about that, but I'm not worried so much about philosophy. I think philosophy will stick around because it's part of, you know, what people need. As you mentioned, it's not only on the sense of breaking a paradigm and exploring, you know, discovering new possibilities, you know, because again, when you put these ideas together, you don't really know what might happen, and something new might come out of that. But also it's part of, I guess, it's also something that we just do all the time, that we need to, even in periods where there's little interest in philosophy, part of what keeps science also alive is just the philosophical interest, even from people who are not philosophers. So I guess even if people tried, I guess that's what I'm saying to say that even if people tried, like, you know, we all know that there are scientists out there who also want to be very, you know, they want to make a clear-cut distinction between philosophical and scientific activities, but we know that they are not going to succeed because they never have, you know, these things. As we're going to see with Einstein, you know, or with Leibniz and with Newton, these people just were going from philosophy and science systematically. You know, some of their main arguments, for example, the Leibniz case, right, which we're going to be discussing. Leibniz's main reason for his argument against Newtonian absolute space was a metaphysical reason, right? And
Yes.
which was also connected to his religious belief. So these things don't really come apart that easily, right? And but yeah, I mean, we should just bear that in mind, when I mean, not necessarily us, but just everyone, that well, philosophy is not going to disappear. These, you know, these types of discussions are not going to go away, even when people don't show that much interest at a certain period of time. Yeah.
Yeah, they're always lurking.
But
Maybe it'd
anyway,
be worth turning to the text.
yeah. I mean, I
Maybe
guess
it's
so. Let me just, I guess, give you a sort of breakdown of what I thought some issues that I think it's either worth highlighting, or I'm confused about, or I wonder what your opinion is. So I just like
yes.
give a general idea of the chapter, right? So the chapter uh, starts by Friedman discussing his part of his interest in the subject, and then one of the things that he mentions was that when he was studying with people like Grunbaum, conventionalism about space and time was still pretty much the dominant philosophical paradigm. And then conventionalism about space and time, if I'm representing the view correctly, is just the view that you know, some of the properties that we ascribe to space-time are merely conventional, so that they don't really they aren't really properties of the space-time itself, but they are just ways in which we decide to frame our theories for ease of use. And one of the things, I mean, we're going to go through this in more detail, but one of the key conventionalist discussions has been about, you know, the metrical properties of the space-time, you know, for example, how, you know, a metrical fact is how far apart am I from this computer, for example, right? That's a metrical fact about this local region of space-time. And another one is, you know, how far you know, what's the space-time interval, or how far apart are, you know, my being here talking to Tim from, you know, the Obama's victory, right? The first Obama victory or something like that. So those are questions about metrical questions about space-time. And then people like Grunbaum were saying following Reichenbach and others, that many of the views about the metric are really conventionalist. There's not really a metric to spacetime. It's just a conventional choice. Of the geometry is part of a conventional choice. So that's one thing that led Friedman to his interest in the subject, because he saw this new book that was published. I think he mentions Anderson, someone called Anderson. And he said, and it seems that that book showed what was misleading in this picture, that general relativity doesn't really support this narrative, that the conventionalist narrative, that there's like a realist reading of general relativity where spacetime does have, that, for example, the metric of spacetime is something which is, not conventionally chosen, something which is out there, and so on and so on, right? So that's like the point of entry for Friedman. And then he, part of what he tries to do is just like give a setup of what was like the historical position on the subject at the time, and then go through like the main points of the historical narrative of how space-time theory came to be developed. The Newtonian arguments, the Leibnizian arguments, the switch to special relativity, and the switch to from special relativity to general relativity, and what they involved in terms of structures of the geometry on the one hand, and the structures of the transformations of coordinate systems on the other, and the relations between those. And then having gone through that, he then goes back to the logical positivist issue, and says what he thinks they had in mind, what he thinks they were wrong about, and what he thinks what the import of the discussion is. So, I mean, that seems to be like tell me if I'm missing something, but I think that's like the general content of the chapter.
Yeah, I think so. Well, I think there's a narrow and a broad look at the chapter, and I think you just described the narrow look. The narrow question is, does the general theory of relativity support a relational concept of space? Is it consistent with a conventionalist account, or is it consistent with a realist account? Can we answer those questions by appealing to the general theory of relativity? I think, and that does fill most of the text. But there's a broader thing that comes out at the end of the chapter, which, in fact, I think you already mentioned.
Mm-hmm.
On page 30, where he says, oh, perfect.
Yeah, let me, sorry. Let me.
Yeah, if you can get to
Page 30, right?
Yeah, and go down to the paragraph that says, here we can use.
Mm-hmm. Here it is.
Yeah, I think this is the bigger view. Here we can use the development of relativity theory to advance beyond positivism. A central problem facing post-positivist philosophy of science is theoretical underdetermination. The problem of elucidating, and perhaps justifying, methodological criteria for choosing between incompatible theories that are empirically equivalent or agree on all observations. Such criteria will ipso facto provide a distinction between good and bad theoretical entities. An entity is good, its postulation is legitimate, just in case it is postulated by a methodologically preferred theory. I shall show how the evolution of relativity reveals these methodological criteria in action, allowing us to drive a wedge between good theoretical entities postulated by methodologically well-behaved theories and bad theoretical entities postulated by methodologically ill-behaved theories. Most important, we shall see what is good about the former entities and theories, what point or function they serve in the process of theoretical inference, explanation, and confirmation, and what is bad about the latter entities and theories, how they are pointless or superfluous in this process. I think that's the broad view. And I think this goes back to what we were talking about earlier as the general theory of relativity as kind of a paradigm for what a rational understanding of nature would be like.
Right.
As science progresses, we learn more about how to do science. And I think that this is kind of the bigger implication. You know, whether you are a conventionalist or a realist about space-time, you still would like to understand what kind of theoretical entities to postulate and which ones are methodologically well-behaved and which ones are degenerate.
Right, right. Yeah, so I guess, I mean, yeah, I mean, I guess two things to say that I like to say here is the first is something that I mentioned to you earlier, which is there's still a lot of obscurity, even though, you know, some of these methodological ideas of trying to, so for example, one of the underlying insights that Friedman has here is that when it comes to the history of space-time theories, their development showed that there was a willingness from the physicists working on these theories to get rid of redundant structure, right? So, and the typical case here is the case of absolute rest, right? So, for example, Newtonian spacetime, as posited by Newton, had this distinction between absolute rest and you know, sorry, absolute motion and relative motion, right? So, you know, objects, relative motion, we can talk about where an object is located, or what its velocity with respect to another object, and that makes perfect sense. But in Newton's theory, you could also ask questions about what the absolute velocity of an object was, or whether the object was at rest, like absolutely at rest or not, for example, right? Those were questions that you could pose about the geometry of Newtonian spacetime. And then that's like the typical example, right, that Friedman focuses on, but obviously there are others. But then the point is that physicists noted from Leibniz onwards that this distinction between absolute position, absolute velocities and relative velocities, and you know, whether an object was absolutely at rest or not, were absolutely of no use for the empirical content of the theory. There was no way of empirically detecting an absolute frame versus an absolute rest frame versus a relative rest frame, and the same for velocity. So, physicists sought a version of space-time theory which got rid of those, you know, redundant structures, right? And then that was just an example, right? But it was important to just keep some sort of example of what he's thinking about when he says something like this. And then part of the claim here seems to be that that's good practice, right? Like, it's good practice in science to get rid of redundant structure or posits that don't do any useful empirically, give us any useful empirically distinguishable content. And that's connected obviously to the idea of theoretical posits and whether they are good or bad. So in this case, for example, absolute positions will be a bad posit, something that we need to get rid of, but there might be other posits in the Newtonian theory that are good and we need. And I guess we have, I mean, in general, we can say that we have a grasp of why we call that good versus bad posits, but it's still philosophically, I don't think it's still as well understood what it means to be a good posit or a bad posit. I mean, I think that these responses that I just gave about whether there's empirical distinguishability or not, I think that I mean, that sort of gives us part of the motivation, but it's not really an explanation for the good versus bad theoretical terms distinction. Or what do you think, Tim?
Yeah, I think you're right. There's definitely more to be said about it than just that. I think the two you were mentioning before, empiricist arguments, and there were two empiricist arguments that he mentions.
By the way, do you want to just before going or that, do you want to like say something about you know like what's the idea behind relationism and the idea behind the realism about space-time view, like broadly speaking?
Yeah. Well, the two classic positions, of course, are Newton and Leibniz. And in Newtonian mechanics, space and time are thought of as absolute. So they're kind of objectively existing entities on their own, like a stage in which all events take place. And so space is kind of like a fixed stage. And then there's time, which is also absolute. You could almost think of there being like God's wristwatch, and that determines when things take place and when things don't take place, or not determines it, but scratch that. And so in Newtonian physics, the there's a distinction between absolute and relative motion. Absolute, you have an absolute location because space is what it is, and you can have an absolute location in it. And then you can have a relative location, which refers to another reference body.
Mm-hmm.
And that also gives you a notion of both absolute and relative motion. You're in absolute motion if you move from one absolute location to another absolute location. And you're in relative motion if you move from one relative position to another relative position, where both of those relative positions are specified by a certain reference body.
Right, and this will be the inertial frames.
Yeah, well, I was going to add to what you were saying that there's a kind of conceptual awkwardness to Newton's position, although it is perfectly self-consistent.
Mm-hmm.
The question is, for Newton, in which reference frames are the laws of Newtonian mechanics valid? And those laws are valid only in inertial frames. If the frame is accelerating or in rotation, then those laws are not valid. If you try to apply Newton's laws of motion in a rotating reference frame, you'll find that they do not work. That's why we have the language of fictitious forces when you talk about centrifugal forces or Coriolis forces. They're not really forces because they're not the causal effects of other bodies. They are, so to speak, apparent forces that are artifacts of the particular coordinate system that you've chosen.
Mm-hmm.
So for Newton, it was necessary to postulate absolute space because it's only in the absolute rest frame of the universe are Newtonian laws valid. And for any coordinate system moving under its own inertia. And so he felt compelled to postulate this absolute space in order to say in which frames of reference the Newtonian laws are valid.
Right.
And here, and that's a little bit of an awkward position because, as Einstein says, what does nature know about our coordinate systems? A coordinate system is just a way of labeling events in space-time. And so he's kind of motivated to get rid of this awkwardness that absolute space and time present in a generally covariant theory, where the laws of physics are the same for any observer, regardless of their state of motion.
Right. Right. Sorry, I think you were saying, I do have something to say about this, but you were about to say something else, right? That I didn't let you finish before.
Oh, I forgot to mention how Leibniz fits into this.
Mm-hmm.
Because Leibniz appeals, as Friedman says here, to indistinguishability of the different inertial frames, and parsimony as kind of critiques. But when Einstein looks at this later on, he says that, well, kind of Leibniz was on the right track, but at the time, his ideas could not be made good. His critique could not be made good, because it is true that in Newtonian mechanics, you can distinguish between an inertial frame and an accelerating frame. And if there's such a thing as absolute rotation or absolute acceleration, you seemed to be forced to postulate absolute space. But it's a weird postulation, because you're singling out the inertial frames as special.
Right.
Why isn't there just one frame, the cosmic frame? Why is it the cosmic frame plus all the inertial observers in addition to the cosmic frame? I think that's part of the story too.
Yeah. I mean, so I guess, I mean, I had like a couple of things here to add. So, yeah. So, for example, I guess like one thing about the Newtonian theory is he does try to, for example, as he mentioned, he was standing in the shoulders of giants. So he does try to save like these Galilean intuitions about the special principle of relativity. So the idea that, for example, if that there is these two different kinds of frames, right? So, and I think, I mean, one of the definitions I've seen of inertial frame is just one object, a sort of physical object, such that all the parts of the object are at rest relative to each other. So that's like a sort of, I guess, intuitive definition of inertial frame. People talk about rigid bodies, which I guess is sort of like another way of matches that intuition. But then I guess part of the idea is that, for example, you can imagine, or we have all been in these kinds of experiences, right? You are driving a car, or you are in the passenger seat, and if the car is moving at a constant velocity, then you can be playing with, a ball or whatever, and you might not feel, you might feel as if you're at rest in a sense. The only way in which you realize that you're moving is if you are seeing, trees passing by or whatever. But if you were sleeping or in the dark, you might not feel any difference. But then if suddenly the car gives up like a turn, or it starts accelerating, then you start feeling your body being pushed and pulled in different directions. So, and that's part of, I guess, like part of the intuition behind, I guess, the idea of distinguishing these types of frames, recovering that distinction in physical theory. And Newton, I mean, I guess part of the issue here, I mean, philosophically, at least as the way in which people tell the story, for example, like people like Motley or Dasgupta, etc., is that the problem with Newton's theory, like the biggest problem with Newton's theory, was not so much that you had this distinction between absolute and relative motions, because, for example, because of stuff like the bucket experiment, right? So like you have the idea, you have this bucket, you start rotating the bucket. Uh, initially the bucket starts spinning, but the water is at rest relative to the bucket. Then the water starts spinning too. They are both spinning, and eventually the bucket stops spinning, but the water is still spinning. So, but then according to the relationist view, in order for that to be explained uh, by, in terms of relationism, you will have to explain the motions of the particles of water, I guess, in terms of the motions of the motions of the bucket. But that explanation is not going to work in the bucket case, because uh, you're going to have motions in the circular motion in the water receding from its axis of rotation, and you cannot relate that. You cannot explain that in relation to the the outside of the bucket itself, and say that that's caused by that relative motion. Uh, so because of that datum, is that one of the motivations for Newton in his Principia to posit absolute motion. But that seems like a certain type of absolute motion, right? Like acceleration or rotation is a certain type of absolute motion, which is distinct from absolute velocity or absolute rest, right? So it seems like the typical complaint, for example, from people at, attacking Newton, this was not so much that he posited some absolute motions, but that he posited more absolute motions that were required to save the dynamical phenomena, or to vindicate his laws. And that's why you get all these fictitious forces. Um, so, uh, so I guess that's one of the complaints.
I think I only partially agree with that telling of the story. I guess it's inevitable here to bring up the idea of Mach's principle.
Right.
The way I look at Mach's principle is that Mach was trying to explain the origin of inertia.
Mm-hmm.
Inertia is still not understood today. It's just a fundamental principle.
Mm-hmm.
But Mach, and I think the development of the general theory of relativity, is trying to teach us something about the nature of inertia. So in the case of the rotating bucket experiment, the water recedes up to the sides of the bucket, and that's a manifestation of the bucket's inertia and the water's inertia.
Mm-hmm.
And in Newton's thought experiment, he abstracted away from the rest of the cosmos,
Right.
As if the earth and the bucket were just kind of out in an infinite void by itself.
Mm-hmm.
And Mach says that, when you do the thought experiment this way, you've snuck in another assumption. You've abstracted away from the rest of the universe. And that really there's all the distant stars and nebulae, and you could be rotating relative to the nebulae. And so he, not very clearly, I think, postulates that the inertia of a body is the result of the total distribution of matter in the universe.
Right. In relation to its to the fixed stars as well.
Yeah, to the fixed stars. So there's a deeper question there is, what kind of property is inertia? For Newton, he's basically assuming implicitly that inertia is an intrinsic property of the body,
Mm-hmm.
Independent of anything else in the world. It's just an intrinsic property of it. Whereas Mach is kind of making inertia itself relational, and that the body has inertia because there's all these other bodies around somehow.
Right. Yeah, and as we will see in this chapter, one of the motivations for Einstein that Friedman thinks was a mistaken motivation, or was the idea that you could recover something like the Machian principle in general relativity, because in general relativity, the metric is given by the interplay between masses or matter and spacetime, right? Like the metric tensor is just gives you there's this functional relationship between the amount of mass, the amount of matter in the spacetime region, and the curvature of the region. And it seems like since you're going to account for gravity in general relativity in terms of the curvature of spacetime, it seems like you can give explanations of some of the absolute, or at least that seems to have been Einstein's original intuition, that you could give explanations of absolute acceleration or rotation in terms of something like the Machian principle, because you were going to be relating those absolute motions to the mass distribution of the matter distribution in the universe. But part of what Friedman points out, and maybe we can come back to this a bit later in more detail, but part of what he points out is that doesn't really make acceleration and rotation relative to the mass distribution, because at the local level, it's still the case that you can still, you're not going to have a distinguished class of frames, but you're still going to have a distinguished class of geodesics, the free-falling geodesics, which are going to give you the locally inertial, he calls them locally inertial geodesics, or locally inertial frames. And in those, you can still talk about absolute acceleration and absolute rotation. So that's part of I guess the claim, but I guess it's connected to the Mach principle because of the motivation Einstein had. So I'll ask you about this in a second, but I guess something else that I just wanted to say to finish the, I guess, like the typical reconstruction of the Newton story was that, going back to what you said about Leibniz, right? So Newton, at least, as you said, I think that this is completely right, that you're saying that Newton assumed that you could take everything from space, and then at the end, to explain, the bucket experiment, you need to posit something like absolute rotation, right? Which Mach thought was illegitimate. But he also has this other thought experiment, which is worth mentioning because, in a sense, it's easier to follow than the bucket experiment, which is the rotating globes experiment. And for this experiment, he actually straightforwardly doesn't takes away everything from the thought experiment. So he just says, imagine two globes rotating around their axis of motion, right? Given the fact that the only things in that world that he's imagining are the two globes, then the relation of every part of one globe to the other is going to be the same, regardless of of the motion of the globe, right? Regardless of the rotation, or etc. Right? So they're always going to preserve the same spatial-temporal relations. However, if we imagine that we can imagine that the globe is actually rotating versus non-rotating, if we are able to conceive of the rotating globes as having a chord between them that has some tension, so the tension will reveal the rotation versus the non-rotation of the globes. But as mentioned before, there's nothing in the relative positions that could explain that. Therefore, you have to posit some sort of absolute motion. But again, I'm just mentioning this just for the sake of the illustration, because it's very, I think, useful and easy to understand. But this thought experiment suffers from the same assumption that you mentioned before, that it straightforwardly takes away everything from the cosmos. And so I guess part of, as you mentioned also, which I also wanted to comment on, the Leibniz arguments, right? So Einstein seemed to think, as you mentioned, that there was something to these arguments. Many people still think that there's something to these arguments. I am sympathetic to these arguments as well. But Leibniz introduced these arguments in the context of his own metaphysics, his own religious beliefs. So he had further commitments to uh, that forced him to reject the Newtonian picture of the world, right? So, for example, some of the two principles that he used were what is called the identity of indiscernibles. So, the idea that for any x and y, if they are qualitatively identical, if they have shareable qualities in common or properties in common, then they are identical. And on the other hand, the principle of sufficient reason, that if something happens, if P is the case, then there has to be a reason for P to be the case. So it seems like for Leibniz, these two arguments reinforce each other in rejecting the Newtonian picture. So if you don't mind, can I go quickly through one of his arguments just to show how that
Yeah,
works?
let's rehearse the arguments because they're directly relevant to everything we're talking about here.
Right. So let me rehearse one, and then maybe you can comment on that. So for example, this is, I guess, the easiest one, but it has to do with it's what is called the shift argument. So imagine the world, like every material object in the world, it's a Euclidean world, so it's the world at a time, for example, right? So, like I am at a certain distance from my laptop, and this stuff is, right in front of my face, etc. So we could imagine every material object, or it's possible for every material object, if Newton is right, to be shifted to the right 3 meters, for example, right? And if every material object is shifted to the right 3 meters, then because that's basically an isometry, it's just like a rigid translation. It's going to preserve all the distance relations between every material object. So it will be empirically indistinguishable from the world before the shift. However, if that's possible, that goes against the two of Leibniz's principle, right? So because those two worlds are qualitatively identical, at least when it comes to observability, to qualities that are observable, then those two worlds should be identical. They should collapse into one single possibility. And for the principle of sufficient reason, the worry here is that if God could have, so God needs a sufficient reason to do something instead of something else, right? Because God is good and God does the best. So if God put the world in a set up the world in a location in space-time, but that location is exactly like any other shifted location, then it seems like there was no sufficient reason for putting the world in that location instead of the other. So given those two, so the Leibniz shifts violates both the principle of sufficient reason and the identity of indiscernibles, which are like a priori truths of reason. Therefore, they are impossible. But possible according to Newton, therefore Newton is mistaken. That's how I would put them.
Yeah, I guess there are two things I wanted to say. Stepping back to the rotating balls.
Yeah.
There's another question you can ask about. You can ask about the relationality or the absoluteness of space, but there's also the question of time. How do you determine the passage of time in that world? And how do you determine whether it's going forwards or going backwards?
Right.
There's a
Yeah.
question of the sense of time.
Mm-hmm.
For the Leibniz thought experiment, I think I'm inclined not to be impressed by the argument. I think it makes very clear what he means in his relational picture. But the reason I'm not impressed is that it seems to me a matter of fact as to whether space has translational symmetry or not. Aristotle, of course, didn't think that the universe had translational symmetry.
Mm-hmm.
There was a privileged point, the center of the universe, and he had a mostly self-consistent view about the physics of that world.
Sorry. Could you just like quickly mention what translational symmetry is? just like in one
Oh,
line,
okay.
just for
So
anyone
in
who
one
doesn't.
line, translational symmetry means this. I can do an experiment at one part of the universe, and then I can perform the same experiment elsewhere in the universe, and I'll get the exact same results for both experiments. Um, that's the kind of modern way of expressing Leibniz's idea.
Mhm.
And today we believe in translational symmetry, that the laws of nature are the same everywhere in the universe. Which means if you're in a science fiction story and you wake up in some strange place, you might ask yourself, where am I? Well, if you're allowed to look out the window and have a telescope and can look at the stars, you can find out where in the universe you are.
Mhm.
But if you're trapped in a room and you're not allowed to look outside, what can you do? Well, you could try to perform experiments, measure the mass of the electron or Newton's gravitational constant G or check Faraday's law of induction. And if translational symmetry is valid, there's no experiment you can perform in this room that will tell you that you're on Earth and not on not near Alpha Centauri or in the Andromeda galaxy. So the laws of physics are the same everywhere.
Yeah.
But that's an idea that sort of begins with Galileo and Descartes. For Aristotle, there is a privileged point to the universe, the center of the universe, and the motion of all bodies depends upon where it is. So if you're a little particle of fire, you know which way to go from your own internal, teleology. You're supposed to flee from the center of the universe. And in fact, there's a whole distinction between the sublunar world and the superlunar world. And that seems to me to be like a self-consistent picture of the world that could have even been true. And I don't think that any a priori argument could show that Aristotle was wrong about that. There could have been a center of the universe, a special point. Um, it's part of the emergence of the concept of space that it's homogeneous. I mean, Alexander Koyré wrote about this. People didn't have this notion that always have the notion that space had translational symmetry.
Mhm. Yeah.
So
Yeah.
that's why I'm not impressed by his argument, and I'm a little surprised that he gives it in a way because, of course, Leibniz knew his Aristotle, and did he just believe that Aristotle was a priori wrong?
I'm inclined to. I mean, I'm no Leibniz expert, but far from it. But I guess I'm inclined to think that in these cases he did reject the Aristotle's views on space and time because he had a lot of confidence in these principles. So I guess, the import of these arguments is that, as given originally because of his a priori assumptions, they are philosophically problematic for some of the reasons that you mentioned. But when they are combined, or when they are seen in the light of what we now know or what we can about about the universe, about certain translational symmetries, they do have some weight in the sense, but maybe not the weight intended by Leibniz, in the sense that there's no theological reason or a priori reason for this to be the case. It just happens to, I guess, it just happens to be the case that, I guess a modern reformulation of the Leibniz argument will be something like qualitatively indiscernible possibilities. Qualitatively indiscernible scenarios are just the same scenario.
Mm-hmm.
We should treat them or regard them as the same, and that does seem to have some appeal, some methodological appeal. It doesn't seem to be a priori true. So, for example, you might remember the Max Black paper on. Have you ever seen that paper? It's like a paper of where Max Black argues against the identity of indiscernibles. So he says, imagine two spheres with two identical spheres which are alone in the world. It's still possible to do that, even though those spheres will be, so for example, any property that you can give of one of them, you can give of the other. So for example, a sphere A is at a certain distance from a sphere B, but by symmetry, it also holds that sphere B is at a certain distance from a sphere A, etc. So they have all so he's thinking about logic, right? So he's thinking every open formula that one of those can, satisfy, so does the other. So if this is what Leibniz meant, then that principle of the identity of indiscernibles is just a false principle, because it's possible for there to be qualitatively indiscernible things that are distinct. So I think that the best or the most charitable way to interpret the argument from Leibniz is not the philosophical, theological, or even logical way, but just a sort of methodological suggestion that.
Oh, perhaps, if you don't mind me jumping in,
No, please.
maybe another way to put it is to say this: Leibniz and Newton agreed about translational symmetry.
Mm-hmm.
And given translational symmetry, then proceed. So that gets rid of the Aristotle problem,
Right.
and a lot of the a priori problems. Maybe that's the direction you're going. Let's take translational symmetry as an empirical fact. Okay, given Leibniz's methodological strategy, he's led by that fact to relationalism.
Yeah.
Is that
I
the
think.
idea?
Yeah. I think. I mean, I guess. So I guess this is what I will say. I guess for Leibniz, the theological and philosophical arguments really did matter. But for people who want to save Leibniz or save the Leibnizian insight, what they care
Einstein,
about
for example.
is what you just said. Yeah.
Okay. I guess we've done a good job at like setting the big agenda. Should we go toward the beginning of the introduction and start working through some of the more historical stuff? We haven't really talked about Kant or Schlick
I mean,
at
I
all.
guess. Yeah, I guess maybe we should. Just, so give me a second.